Good afternoon, everyone. Thanks for joining us on this webinar for Autosar profiling. I hope everyone is able to see my screen. Just raise your hand or send out a message in case you're not able to see the screen or you don't hear anything. I think if everything was right today, we should have ideally had sessions in India, starting from Pune. We would have had sessions today. I think was Chennai and tomorrow was Bangalore. So we had a long actual sessions planned in India, but as the situation goes, I hope everyone is safe with your families. Thanks for joining in. It's a great response. Thank you so much for everyone joining in on this webinar. I will quickly run through a small introduction about Trident Infosol. That is a company that is organizing the webinar today. I will quickly run through. It shouldn't take me more than 4 to 5 minutes, and then I will hand it over to Mr. Felix, who will be conducting the session on the technical aspects today. Right. So just to get started. So Trident, we started operations somewhere in 2000. So that's close to 2 decades of operations in India today. We have operations all over, right from Delhi, Bangalore, Chennai, Ahmedabad. So we have multiple regions that we work with. Bangalore being our predominant operations that happen. We also have another operations in Singapore where we manage all our orders. We are a team about 200 plus today. So that's the team size that we're working on. And today we are known in the industry as a complete embedded solutions provider. So anywhere in Trident Infosol that comes in, so we are known as an embedded solutions provider, be it hardware or software. We are known as that. And these are some of the partial list of clients that we have been working over the years. Again, this is a very small list that I've taken. On the left is the complete DRDO, the defense labs that you see there. On the right is all the corporate customers. If you're not seeing your company logo, I'm 100% sure somewhere we have been associated with your companies, because we have a very big list of clients that we have been working across. Right, and just to talk about the business teams or the teams that we have within Trident, we have 3 major divisions. One is the COTS hardware, there's a COTS software, and there is a system solution group. With these, we are serving various industries, be it automotive, aerospace, medical, just any industry we've been serving across with these. So I'll just walk you through what each division is again very quickly. This is our first group, which is a hardware group. Now they are specialized in selling a lot of single board computers. It could be the small ECUs or LRUs when it goes to avionics, maybe some IO cards, Ethernet cards, storage solutions, everything. It could be mill grade industrial based applications. We also work with a lot of rugged computers like the rugged laptops or rugged tablet PCs, which are mostly used in industrial applications, or it could be some daughter cards, the mezzanine cards, the mezzanine boards. So we work with these as a hardware group. These are some of the companies that Trident is partnered with. These are the previous slide where you saw all these images that I showed across. Those are provided by these companies. So we work with these companies day in and day out, and that's how you get these solutions. And Trident takes care of the complete technical training, ensuring the products are delivered to the customers. So yes, along with the technology. And this is the next group, the COTS software, and this is the team that is actually responsible for organizing this webinar today. There, if you see, we have a complete solution starting from requirements all the way up to your testing. I'm not going to walk through everything, but then just in a nutshell, we have on the left that you see, the leftmost corner is all the companies that we are associated with. The middle section, what you see is all the products that each of those companies are providing to us. Of course, the middle part, everybody knows that's the recycle. And so, yes, so we work with multiple companies like Deso. It could be model on, it could be at the system level, it could be on the modeling, simulation, analysis. And then when you talk about the code implementations, that's when we work with iSYSTEM, the predominant partner who's doing this webinar along with us today. So we work with them. Again, Autosar, we have solutions on Autosar. It could be HMI solutions, or it could again be when it comes to testing. We have a very interesting solution with iSYSTEM. I don't know if Felix already has some part of it that he will be covering today, but iSYSTEM has something very interesting when you talk about test idea, which is a unit testing. Then we also have some hill solutions. So these are some of the things that we work across. And yes, this is again just a quick snapshot of all the partners that we are working with as a software group. And yes, iSYSTEM will be our focus today, because iSYSTEM is the one who's conducting this technical session. So right, and finally the last group of Trident, it is a system solutions group. Here we have our in-house, so we do in-house designs, manufacturing and the complete test facility, everything happens within Trident. The left and the right that you see are all the components and products that are designed, developed within Trident, and those are readily available for purchase as well. So yes, and these are some of our labs that we have. We have a complete facility, could be on the environmental testing, design, manufacturing. So we have a big facility that is there. This is all in Bangalore. And yes, so that comes to the end of my presentation. Just follow us on LinkedIn before I hand over to Felix. You all can follow us on LinkedIn and YouTube because we conduct a lot of webinars, technical sessions on a weekly and bi-weekly basis. So you all can be updated on the latest technology webinars that we keep conducting. So just follow us on LinkedIn and YouTube. You will find a lot of content already available there. Right, so let me hand over the presentation to Mr. Felix Martin. Felix Martin is working as a field application engineer at iSYSTEM. His history with automotive is very extensive. He's been working with a lot of automotive customers. In fact, he started his research with Continental. He was a research student there. So he's been working predominantly with automotive industry. So no one better than him to talk about Autosar concepts today. So he will be taking us through how iSYSTEM is helping customers with the Autosar profiling. So Felix, over to you now. Thank you so much. Thanks everyone for joining in again.
All right. Yeah, thank you very much for the really nice introduction, Paravan. I appreciate it. All right, so let me see how I can share my screen with this tool. Thank you very much. That wasn't hard. So I just click show my screen. I don't know if you can see my screen yet. Let me know when you see it. Here. Okay, now I'm figuring it out. Oh, you can already see that screen. Okay, perfect. And I will just start my presentation. So now I assume everybody can see my starting slide. So if you can't see it, then just yell. So yeah, again, thank you very much for the nice introduction. My name is Felix Martin. I'm a field application engineer for iSYSTEM. I'm located in the US right now. I've been here for a little over 2 years now. Yeah, I have a long background in the automotive industry. As Paravan has mentioned, I started at Continental and then worked for a timing analysis company called Timing Architects, which has been bought by Vector in the meantime. And they focus on exactly that topic that we are going to talk about today, the analysis of Autosar applications with regards to their timing behavior. So this is a picture of me, and this is how I look right now in the home office, drinking green smoothie and trying to stay healthy. I also had 2 surgery 2 days ago, so my face is still a little bit swollen. You can't see that, but yeah, that's just a little impression of how I'm currently doing in the US. I hope you're all staying safe in India too. So let's have a little peek at the agenda first. Or maybe first start with some takeaways or like what you can expect after this webinar. So you will have a general understanding of what timing analysis is about, especially in the context of embedded applications. You will have an idea how to analyze the OS and the RTE of your application, and we will talk about how to do this with hardware tracing. There are also other options that you will learn about. And you will be able to solve and understand your timing issues, and you will also be able to optimize your application based on the data that you will be able to record. So I will start with a little introduction or motivation, why we're even doing that. I call that the challenge. Then we will talk about different kinds of real-time analysis. Trace techniques are ways to do this kind of analysis. And then we focus on hardware tracing in particular, how we can use hardware tracing to get information about the OS and the RTE. So I assume you all have some background in embedded software engineering, but maybe not everybody is familiar with Autosar. So if I talk about Autosar OS, then it's an Autosar operating system. right? Like Autosar, the standard defines the operating system layer, and it has certain components that have to be there in order for an operating system to be called an Autosar operating system. So that's that part. Operating system is usually tasks and ISRs that are of interest for the timing analysis. And then RTE is the runtime interface, right? That's that interface that is used by the different software applications to communicate with each other. And in the RTE level, we are usually interested in the runnables that are actually executed. And we want to be aware of those objects so that we can analyze them. So then we will put all these strings together and see the final result. And I will talk a little bit about how to be able to do this analysis. Like, it's often not trivial. It depends a lot on the microcontroller, on the exact Autosar OS that you're using. So we have a support structure in place. We call those the 3 pillars of Autosar profiling. And so there's like a lot of application notes and resources that can help you to get started. And then finally, we will take a look at the solution of our challenge. Okay, so I quickly skipped over this slide here before. So just that is clear. So right now, all of you people are muted. So during the chat, during the whole webinar, you will not be able to talk, but you can use the chat to ask questions. And then at the end, we will try to answer some of those questions. So feel free to ask those questions in the chat, and then we will answer some of them. And if there are more questions or if there are things that we don't cover, feel free to reach out via email afterwards. Okay, so let's get started by me asking you a question. So who is familiar with the following situation, right? We are all embedded software engineers. So when we get up in the morning, we are motivated, we get some coffee in our iSYSTEM mug, we are motivated to get to work. We have our debugger up and running with a nice active probe here on our AURIX development board. So we are ready to write some code. We are really excited. So we are happy to get started. And then this happens, right? Your program is not loading, WinIDEA is maybe not working probably. It's just everything is terribly slow, and you were so excited to get some work done, but you can't because like everything is so slow and doesn't have a good performance. So luckily you're an engineer, so you know how to help yourself, right? You open the task manager in Windows and you see something like that. Oh my God, there's 1000% CPU load, which of course there can only be 100%, but you get the idea. And then you kind of look at like what processes are running, and you see like, oh, WinIDEA is actually like doing fine. It's not having too much load, but there is these other applications, and they are taking up a lot of your bandwidth. So you go ahead and you end these processes, right? You don't really need OneDrive to sync right now. Then you don't want Windows to check stuff, and you don't need to browse the internet while you're writing embedded code. So you end all these processes, and then WinIDEA gets enough resources, and you're happy again. So you decrease the load on your system, and then the CPU can do what you want it to do, and you can finally work happily. So you may or may not think that this was a funny story, and maybe you're wondering, so how does this relate to embedded systems? And the exact same thing can happen in an embedded application. So let me show you this example. Like, this is an actual screenshot from a customer project in WinIDEA. I just renamed the task so that you can't identify what application it is. So what you see here is a part of the WinIDEA analyzer. That is that module that you use for timing analysis, and it's the timeline view. So the timeline view shows you over time which objects are running in the system. So on top here, we have a tasks node for core 0. So it shows us the tasks on core 0. And then we have a certain task. And then on the x-axis, we have time. And on the y-axis, so to speak, we have all the different objects. So in this case, I have focused on this particular task. And you can see here that a task can be in different states. And these are actually states that are defined within OSEC and within Autosar. And the states here, so the task state model of an Autosar task is usually starts in what's called suspended, so it's not active. Then it gets activated, so it gets activated, for example, by a timer or by an external interrupt. For some reason, gets activated. So in the case of the electrobit operating system here, it switches into the new state. So that means it's activated, that the operating system has to schedule it. And then finally it goes to running. That means it's actually executed, and then it can be preempted by ISRs or by other tasks. If it's preempted by another task, it goes into this ready state. In the EBOS, it's called ready sync, and then it's running again maybe here at the end, and then finally it goes to suspended. So now I hope this is clear. The red color shows that an object is scheduled, like it is supposed to run, but it's not actually running yet. And then the dark red shows it's actually running, and blue is just a special color that shows that a little bit more is going on there. So we would have to zoom further in to see that there's some more red and some more light red. But the clever guys of you and girls may already have noticed this is a 10 millisecond task. Like I changed the name, but I kept the information that this is a 10 millisecond task. And if you look at the timeline here, and keep in mind this is from an actual production application where we recorded this trace. If you look at the timeline here, the task got activated at about, let's say, 55 milliseconds, and then at 100 milliseconds, that's when the operating system actually schedules the task for the first time. So in other words, it's a 10 millisecond task, and we missed 1, 2, 3, 4, 5 activations of that task. And in fact, the reason why this customer contacted us was they had application engineers, and this runnable within this task creates a PWM signal, and their PWM signal was not updated often enough, and they tried to understand why it's not updated often enough. And once we look at this trace, we were quickly able to identify, okay, we have serious load issues going on there, and we will look later into how to maybe resolve this. So the bottom line is really, if you're familiar with these performance issues on your regular computer, this can also happen in embedded systems. And if we fail to notice them, if your computer is slow, you just get another coffee while, Netflix is loading up. But if this happens in embedded applications, real lives are at risk. So we have to make sure that this timing behavior is okay. And this is what today's presentation is about. So let me back up a little bit. At the end of the day, we would like something like that. So this is now a zoomed out view of the WinID analyzer. You can see a lot of stuff is going on, but the main parts I want to point out is here the trace view. So this is some raw data that has been recorded from the microcontroller, and we will talk about how we can record this data. And then we can analyze it, we can like plot it in this timeline, we can show which functions, which runnables are active, and we can see the ISRs and the tasks that are active over time. And once we have that information, we can also calculate different statistics, like what is the load caused by a certain task, like how long is the execution time on average. There are different kinds of statistics. And then finally, in the analyzer, there's also a code coverage view. So I'm not going to talk about code coverage today, but the code coverage analysis is available in the WinID. It allows you to see which functions and which part of your code have been executed or not over a certain sampling or observation period. So the goal is really, we would like to have something like this to tackle this challenge, right? To tackle this timing challenge. So what types of analysis are there? Like I hopefully agree now that like timing is an important concept, especially with the applications getting more and more complicated. So what kinds of analysis do we have? And this is kind of a hierarchy of different techniques, and we can start here in the middle, and then like each outer technique is is more powerful than the one in the inner rectangle. So the easiest thing we can kind of think of is, if we want to analyze our application and we just want to get an idea of like how often are certain functions or certain tasks executed, what we could do is, with the debugger, we could sample the running task or the running ISR variable, the variable that shows us which task or ISR is running, and we can use that to get a quantitative idea of like in which task, in which ISR the CPU is. We could do the same thing for the program counter. So we could use program counter sampling to get an idea which function is running how often. This is a good approach. Of course, it's just quantitative, so our accuracy depends on how fast we're able to sample, but it will at least, if there's a bottleneck somewhere, if a certain task takes way too much load, we will be able to detect that with sampling. The downside of this approach is, if it allows us to detect that there may be an issue, but it doesn't give us a lot of information why an issue occurred, right? If I get the idea that OneDrive is taking a lot of load, I know, okay, it's taking a lot of load, but I don't really know why. So I can't kill the process, but that's not a solution if I actually want to use OneDrive to synchronize my data. So I might want to get more information, more statistics. So that's the next level in the hierarchy. So statistic means you add some instrumentation to the code, and then you log events that are of interest for you and use those logs to calculate certain statistics. So for example, you could, whenever a task state change occurs, you can log that change. You can say, okay, now task A started running. You read out a counter value from a global counter. You remember that value, and then when the task stops running, you read out the same counter, and then you get an idea about the cross execution time metric for that task. And then you can remember the minimum, the maximum, and the average cross execution time over time, and you can get a lot of statistics that way. The advantage of that approach is it's more accurate than sampling. It gives you deeper insights. But then again, if a task executes much longer than you expect, like if the max cross execution time, for example, is much higher than what you expect, you still don't know why this issue has occurred. So this brings us to the final level, to the king class of real-time analysis, so to speak. And that's the timeline. And that's what we actually want. The timeline view in WinIdea is the view that I showed on the previous slide that really gives you the insight. Okay, at point 1, task A starts, and then 2 milliseconds later it's preempted by an ISR, and then that ISR runs for 2 milliseconds, and then the task resumes. So it really gives you all the separate events over time. And if you have these events, if you're able to get such a profiler timeline view, you get really a lot of different analysis techniques. Like you can calculate all the metrics, you can validate requirements, you can calculate the CPU utilization in total over the complete trace duration, you can calculate it over certain periods in time, you can analyze event chains if you're interested in that. You can make sure that the execution sequence of certain runnables is correct. You really get full insight into the behavior of the application. Okay, so this profiler timeline view is really what we want. So then the question is, how are we able to get these information? And the answer to that is called tracing. So historically, there are different types of tracing, and the main ones are software tracing and hardware tracing. Software tracing means you add instrumentation to your application at points of interest, and then at those points you read out a timestamp value like a global counter, you package it into a message, and you log that message into memory. The advantage of that is you don't need special hardware. Disadvantage is you generate overhead, and you have a limited number of trace objects and trace duration because you are limited by the memory that you have to buffer those messages. The other main technique is hardware tracing. So hardware tracing, this is where it gets really interesting. Hardware tracing works by using a dedicated on-chip trace logic. So it's a dedicated part on your microcontroller that is able of recording these events that we are so interested in order to understand the system. And the good thing about this trace logic is also that it uses a dedicated interface, a dedicated trace interface, which is usually a debug interface, to send those messages off chip. That means you don't generate any overhead. You can trace much more objects. You can record much longer traces. So for example, in that customer example that I showed in the beginning where we had the timing issues, we actually had a really powerful setup where we could record for seconds or even minutes if we wanted to get deeper insight. That being said, you need dedicated hardware, like you have to have this trace logic available on your microcontroller. And depending on the microcontroller you're using, you might or may not have that available. That being said, a lot of embedded microcontrollers have a trace logic available, or at least there's a way to get it. And then finally, there's also hybrid tracing, which is really any combination of software and hardware tracing. So for example, there are certain hardware trace techniques where you have to write into a dedicated trace register to generate trace messages. That's called instrumentation trace. And if you have that available, you have to instrument the application a little bit. You generate a little bit of overhead, so it's kind of a disadvantage, but it's a much lower overhead than software tracing. And then the hardware trace interface takes care of sending the data off chip. So any combination of software tracing and hardware tracing, it could be 90% software and 10% hardware, which is not ideal. Could also be 10% software tracing, really small instrumentation, 90% hardware tracing, a lot of utilization of the on-chip trace interface. That would be ideal. So you still kind of get the benefits of hardware tracing. So let's focus on hardware tracing, because software tracing definitely have a place, right, on a desktop computer. Like if I wanted to debug OneDrive, then I would use some form of software trace approach because I have a lot of throughput and I'm not limited by real-time requirements. But in embedded applications, adding additional code is usually not a good idea. So this is why we want to focus on hardware tracing, where we can get insight without being intrusive, without adding instrumentation, or if we have to add, we want to really add the minimum amount of instrumentation possible. So let's focus on that hardware tracing. As I said, hardware tracing relies on a dedicated trace logic on the microcontroller. So we have a setup like this, right? We have a target processor, we have the debugger connected to it, we have WinIDEA. The target processor has one or more CPU cores, and then ideally we have this trace logic available. And you can see the trace logic consists of three parts here. We have program trace, data trace, and instrumentation trace. So those are the general types of trace that are, if we talk about hardware tracing, then we talk about one or more of those three building blocks. So let me explain what those means. Program trace means recording the actual instructions, the actual program counter of what the application is doing. So you can think of program flow trace of really getting the information, which function is executed after another, and then which individual branches are taken. So for example, you get, okay, there's a function entry into function A, and then there's an if statement, and then it calls another function, and then the other function returns, and then a variable is assigned. So program trace really gives you full insight into that flow of the application. The challenge with program flow trace, I want to mention it right away, is that it generates a lot of data. So usually program flow trace doesn't allow you to record for longer periods of time. There are some exceptions, but usually the duration of program flow trace is kind of limited. The next technique we have is data tracing. Data tracing means observing certain areas in memory and then recording all write and read accesses to those data areas. And this is actually really interesting for us. The cool thing is this data trace logics, you can usually tell them what memory areas you're interested in. So you can tell them if there's a certain variable or a certain memory range, you tell them I want to record accesses to those variables. And then whenever you write to those areas, the trace logic will automatically generate a message and will send it to the debugger. And then finally, instrumentation logic is that hybrid kind of technique where you write into a dedicated register or into a dedicated memory area, and then for writes into those memory areas, the trace logic will generate a message, and the message will contain not only the address where you have written to, but also the value that has been written into that area. And the same is true for data trace. You don't only get the information that there has been an access, like a write to that memory location, but you also get the information about the value. Okay, all those three blocks generate trace messages with different encodings. On some microcontrollers, a timestamp is added on the chip, or there may be dedicated timestamp messages. They are buffered and then sent off to the blue box and then finally to the PC for analysis. Just want to point out for completeness sake, on some microcontrollers, the timestamp generation is not done on the processor, but actually inside the blue box. And then once we have that data, so once we have that workflow going, the cool thing is on the PC, we get all the trace messages, we can decompress them, right? Like the trace logic here compresses the message to generate better transmission rates here. It compresses the messages, so we decompress them here, we reconstruct the trace, and then we can do all the profiling and all the timing analysis. So this is how hardware tracing works. And the cool thing I really want to point out again is we are non-intrusive. So these building blocks just passively listen to the CPU cores and to the buses inside the microcontroller, but they don't interfere with the application. So they don't generate an additional overhead. So this is really important to understand. So now I need one more piece in the puzzle to put everything together. What do we actually want to record? And this is important. So for real-time analysis, we usually speak about three main objects, and I have mentioned them, but I will mention them again. On the OS level, we talk on the operating system level, that is, we talk about tasks and ISRs. Tasks are the main containers that execute our functionality, and then ISRs are also containers, interrupt service routines, but they have a higher priority and run in a dedicated context. So tasks and ISRs are really, really important for the timing analysis. And the good thing is the so-called RT file, the OSAC runtime interface file, provides us information about those tasks and ISRs. The RT file was defined in the standard that came before Autosar, actually, in the OSAC standard, but the RT file is still generated and still part of Autosar. So if you're using any Autosar operating system like Vector, Electrobit, ETAS, they can generate this RT file and our debugger can generate it. Okay, so this is important for tasks and ISRs. And then this RT file, without going into too much detail, includes information about, okay, there is a running ISR and a running task variable that we can trace with data tracing, for example, and then we can reconstruct the task and ISR information from that. The next thing is, usually we want to look a little bit deeper into the RTE, into the Autosar runtime interface. And we want to see the runnables and maybe even the functions that are being executed. So RT historically does not support the RTE because when RT was defined, the RTE did not yet exist. That came a couple of years later. So iSYSTEM has a proprietary iSYSTEM profiler XML format, and with that format, we are able to make WinID aware of runnables and functions and other objects in the system. And in this talk, I don't have enough time actually to explain how to generate this iSYSTEM profiler XML, but I will point you to some further resources that you can use to understand that better. And then finally, what I also want to point out is Autosar operating systems and the RTE provide hooks that allow you to add instrumentation to the operating system and to the RTE. And in some cases, when we can't do a pure hardware trace-based approach, we might need those hooks and instrument them, and then we are able to record this hook instrumentation. So this is the way how we get awareness of the operating system and the RTE. And then by now, it's actually, we have covered a lot of information, and I kind of want to put together the whole thing with this slide here. And it might look intimidating at the beginning, but it's actually, you are familiar with all the concepts that are on this slide. So on the left side, I have listed the different trace techniques that we've talked about. Program flow trace, data trace with some instrumentation maybe, and instrumentation trace. So that's the left side. And then on top, we have the different trace objects that we're interested in. So we have task ISRs. We might be interested in only the running task. We might be interested in the task states. We might be interested in runnables. And we might be interested in more complicated objects. I call them signals here, which could be variable accesses, RTE communication, semaphores. So the question, if you start with timing analysis, usually where you want to start is here with the running task and running ISR. That is really the hello world of timing analysis. So you start with running task and running ISR. So you generate a RT file, and then hopefully you have data trace available, and then you record a running and task and running ISR trace, and you can get the first insights into what tasks are running, what ISRs are running, what are the different loads. But then there are other kinds of techniques. So for example, if you want to get the task states, there might be ways to do this via the RT file. There might be ways to do this via instrumentation. So for different use cases, there are different solutions, as you can see. So green shows it's possible, and we have it well documented and supported. Yellow means it's limited to a certain degree, but it's probably not ideal. So for example, recording runnables via program flow trace is definitely supported, but it's also very limited because, as I said, program flow trace generates a lot of data. So this is why I give this a yellow box and not a green box. It is possible. So for example, with the customer that I mentioned, they have a high-speed trace interface available. So we are actually able to record all the functions on a specific core for multiple seconds. But that's a really powerful setup. It might not always be possible. So the bottom line is, it's not trivial, unfortunately, but some use cases are trivial. So if you're in one of the green boxes, then we can help you really fast. If you're in one of the yellow boxes, we have the expertise to help you with a little bit more effort. Like one of the experts of Trident, for example, they will be able to support you. So let's have a look at the 3 pillars of Autosar profiling. So I just want to repeat the message one more time. Before you start with this whole real-time analysis, you have to be clear about what you even want to achieve. Sometimes recording running task and running ISR is totally fine. Sometimes you need to get deeper insights. You need the runnables and the signals. I recommend start with running task and running ISR. This is already really, really helpful, and then go into more detail. If you want to go into more detail, then we have this support network available. We have those 3 pillars of Autosar profiling available. And the first pillar is on our homepage. We have a lot of application notes that cover profiling for different operating systems, vector, electrobit, and so on. We cover different objects like tasks, ISRs, and runnables, what you have to do in order to trace those different objects. And they really go into a lot of detail and give you all the background information. Then we have a script or a set of scripts called ITCHI. It's the iSYSTEM trace configuration helper, and that helps you to generate configurations for some of the use cases. You may or may not need that. And then finally, we also provide consulting. So we are here in the US and in India, our distributor, of course, and then also in Europe. We are really, our engineers are there to help you, so you can reach out to us and ask questions. So that's what the consulting is for. We can really help you to get up and running. And then hopefully at the end, you have something like that in WinIDEA. You really have a profiler timeline and you get the full insights into all the functions, all the runnables that are running in the system. You get a few of the tasks, and not only the tasks, but also the states of the tasks. So you really get full insight into what the operating system is doing with regards to scheduling. And then, of course, you also want to see the ISRs. And once you have that available, you are able to do all these kinds of timing analysis. You can analyze the execution times. You can make sure that your CPU utilization is okay, and you can do event chain analysis. And we actually have a whole other tool called the WinIDEA inspectors that allow you to do a lot of other types of analysis. Inspectors are probably a topic for another webinar in itself. So that's ideally, that's what we want to get. And let's go back to our initial problem statement here. Remember, we had this 10 millisecond task and it was executing only, in this case, every 50 milliseconds, right? So we missed a couple of activations. And it was not really clear, like, why is this happening? We only could see that the functionality of the application was not as expected. The PWM signal got not updated often enough. So we got some functional errors. We were able to pin it down to this task, but why does this actually happen? And luckily, we really get the information of the whole system. So we were able to analyze all the other tasks, and one task that stood out is this customer com task 5 millisecond, and you can see that it's in the running state for a significant amount of the time here. Like, it really puts a lot of load into the system. And maybe I give you a second to take a look here, but see if you can notice something. And keep in mind, new means that a task is activated, then it runs for a certain time, and then it's suspended. And you can see in the name here, this task is supposed to execute every 5 milliseconds. And here, up here, you have the time scale. So from here to here, for example, this is 10 milliseconds. And now if you look down here, see here the task is activated, here it is activated, here it's activated, here it's activated, here it's activated, here it's activated. You can see this is not actually every 5 milliseconds. Like 5 milliseconds would be 1 activation, 2 activations, 3 activations. So for some reason, in this particular case, something went wrong during the OS configuration, and the 5 millisecond task gets activated by the operating system every milliseconds. There are some misses here, but in general, this task is executed much more often than it should be, which increases the load onto the system significantly, and eventually leads to this other task that has a lower priority to not being executed often enough, okay? So we were able to figure that out, and that allowed us to update the configuration, put it into the right raster, into the 5 millisecond execution raster, and then that decreased the load on this task, and the 10 millisecond task was able to execute as often as it should be executed, and that resolved the PWM issue. And you can figure that out without any tracing. You probably can, like, you can do some oscilloscope toggling, you can toggle some pins and so on and so on. But I assure you, if you have this profiler timeline view, it's much more easier, and we were able to resolve that issue really quickly. And then finally, the customer could continue to work without worrying about this timing issue. So this is one example how this trace analysis can give powerful insights and really resolve real-world issue. And with that said, I'm at the end of my presentation. I hope you have a general understanding of real-time analysis now. And let me point you to some further resources. So in general, on our homepage, we have a lot of training material for WinIdea and TestIdea. We have mentioned TestIdea in the beginning. So TestIdea is our unit test tool. It also has some timing analysis capabilities, but if you want to dive really deep, I wanted to show this slide here. If you dive really deep, we have our application notes. So if you go to iSYSTEM.com and then application notes, there you can find the information about vector profiling, electrobit profiling, and we also have an application note about ETAS operating system profiling soon. And there you can get all the insights, like all the different techniques, and you will be able to learn which technique is the right technique for your particular problem. And with that being said, I want to thank you very much for your attention. Again, I hope you learned something new during this presentation, and we and also our distributor team in India are looking forward to hear from you and help you to tackle your real-time analysis challenges. So thank you very much, and with that I give back to Pravin, and maybe we have some questions. Nobody's here. Everyone left. I hope you guys even heard me for the last 1 hour. Pravin, are you here?
Yeah, Felix, I'm here.
Okay, good. So,
right.
I don't know. This is the chat, right? I don't know. Have you seen if you have any questions to answer?
Give me a second. Okay, I'll read out the question for you. Do we need any special license to get this tab or profile timeline in WinIdea?
Yes and no. So to open the WinIdea analyzer, you can look at it without a special license. But if you want to record a trace, there is actually a dedicated trace license for tracing on a different microcontroller. So the answer is yes. If you want to do trace recordings, then you need a dedicated activation key. So it's a one-time activation key, and then that allows you to utilize all the trace capabilities that your microcontroller has. But yeah, that's a good question.
Right. So I have another question from Mr. Naresh. His question goes like this. Can we also do the same trace for tasks scheduled like dynamic kind rate, monotonic, or deadline monotonic scheduling?
Yes, the trace does not really care what type of scheduling algorithm you are using in the background, as long as you have some, like if you're not using an Autosar operating system, but let's say your own scheduler, all you need is some way of telling the profiler which task is running at a certain point in time, right? If you are able to to log that information into a variable, and like most operating systems already do that, then you can record it, and it really doesn't matter what scheduling algorithm you're using in the background. But that's a good question.
All right, there is another question from Mr. Naresh. Are there any limits on the number of event logs? Meaning to say, presume it depends on the number of hardware interrupts that can be enabled on the controller.
Yes. So that's a really good and very legit question. So I understand it, like, what is kind of the limit of the amount of objects and also the duration that I can record for? And the answer is, it depends. It really depends on the trace interface that you have available. So depending on the microcontroller that you're using, if it's an Infineon AURIX, for example, it has the so-called MCDS, that's the multi-core debug system, that's the trace logic on the AURIX. It's really powerful, and it has a lot of comparators for different events, for different data areas, for different program execution areas. So you can use that to really observe a lot of different objects and be really particular with what you want to record and what you don't want to record. So that's the top end, so to speak. And then the bottom end is there are some microcontrollers, and nothing particular comes to mind, like maybe like a S32K, like with the Cortex M cores, where you, for example, have only 4 data comparators. So you can only trace 4 different variables. You cannot even record memory ranges, just 4 simple variables. In that case, you cannot record an arbitrary amount of objects, but then again, 4 variables is usually already powerful and gives you deep insight. So that's one part of the answer. And then the other part is, even on the AURIX, where you have this powerful trace configuration available, the bottleneck is usually the on-chip trace interface. So if you record your trace so that it records really a high amount of objects, and then your event generation rate is really high, you generate a lot of trace messages, your buffer on the microcontroller might run full really quickly, and you cannot record for a long period of time. And then again, in this case, there are high-speed trace interfaces, but the answer is, it really depends. But as soon as you have trace available, you will get a lot of data out. Sometimes you have to compromise a little bit, and we can help you to determine what types of analysis you can expect to do with a certain microcontroller. But yeah, excellent question.
All right, so there's another question from Kiran Acharya. Shouldn't the trace mechanism be disabled during the production? Otherwise, it will keep the back door of the system open.
Yeah, very, very good point. Of course, the trace logic shouldn't be activated during production. So there are different cases here. So for example, for the Infineon microcontroller that I just mentioned, they have production and emulation devices. So the production devices of the microcontroller usually don't even have this trace logic. But there are some microcontrollers where you have the trace logic even in a production type chip. And in that case, it is disabled. Like usually when you go into production, the whole debug and trace logic is deactivated and cannot simply be activated without any password. So often it's sometimes it's even disabled permanently by burning some fuses. So really good point. Of course, once you are in production, this trace interfaces are not longer available, or at least are disabled.
Right. So there is another question from Dibadatta Patra. Do we need to have separate license for activating profiler?
So the profiler does not need a license, but like the trace capability for a certain microcontroller needs the license. So if you want to use the profiler for a certain microcontroller, then you need a trace license for that microcontroller.
Right. So this question is from Harish. What is the difference between OS, EK, and Autosar?
Can you repeat that? OSEK?
Yeah, and Autosar.
I'm not fully sure if I understand it correctly. So OS is in general stands for operating system, right? And there are different types of operating systems. So of course, like Windows, for example, Windows 10 is a desktop operating system. And then in the embedded market, there are there's, for example, FreeRTOS, which is an embedded real-time operating system. And then there's also Autosar real-time operating system. So Autosar OS is a special kind of operating system that adheres to the Autosar standard. So examples for that are Vector Microsar, Electrobit Autocore, ETA's RTA operating systems. So those are dedicated Autosar automotive operating system. So the answer is an Autosar operating system is a special automotive operating system that has certain features that other operating systems may not necessarily have, or at least in a well-defined form. Yeah, but good question.
Okay, so I have a couple more questions. This question is from Santosh Kumar. So his question is, how it is different from vector RTM module?
Oh, that's a really good question. So maybe I kind of want to go back to one of my slides to answer that question. So the vector RTM module is exactly in this class of analysis. So it uses some instrumentation to calculate statistics, and it can also, I think in some versions even can like create a short software trace. But the problem with the RTM module is you get out some statistics and you may be able to see that the task load for a certain task is too high, but then how do you analyze it? So that's really the difference. The difference between the RTM module and Vinadier trace is that the RTM module gives you really statistics only, whereas once you have trace, you get full insights into what tasks and functions are executed over time. So once you detect that the load is too high, as in our example, you are able to look into the profiler timeline and to see like why a certain task was preempted or is causing issues. So that's really the difference between statistics and timeline. That's a really good question. The RTEM module, nevertheless, it's a good module. Gives you some insights, but then the timeline is much more powerful than just the statistics.
Okay. There's another question from Mr. Aditya. His question is, can we do profiling using JTAG interface?
Yes, you can do that. There might be some limitations. So it depends on the microcontroller, but in some cases you are able to do profiling via the JTAG interface, and that's in cases when the microcontroller has a so-called on-chip trace buffer, and in those cases you can then record into that buffer and read out the data via the JTAG interface. The downside of that approach is that the traces may not be too long, but you may be able to record some data. So yes, in general, it's possible. And then there are also often other techniques to get more data out, but then that's microcontroller specific. So for example, if you have a Renesas microcontroller that you're connecting to, there's a so-called LPD4 interface that allows you to get more data out under certain circumstances. So in general, the answer is yes, but with some caveats and limitation.
Okay, so this question is from Rishi Kumar. Can I use this with multi-link BDM debugger?
No, so this type of powerful analysis, I would say you can only do in Vinadier, and you definitely want to use Vinadier and a blue box in order to use the full capabilities of the trace interface.
All right, so we'll stop with this question. I think we're running out of time. The last question is from Shiva. Can user-defined functions be measured apart from OS tasks and ISRs, sorry? And can we see and measure CPU load per core?
And so, yes, so two very good. I think it's kind of two questions in one. So two very good questions. So yes, you can also measure user-defined functions. So you can either do this via program flow trace, or you can add a little bit of instrumentation, like you can write into a global variable at the beginning and then the end of your function, and then you can trace that variable, and then that allows you to see the execution of your function over time, and you can kind of see your functions in this code view here. So that's the first question, and then I think the other part was about CPU load, if I'm not mistaken. So yes, you can, once you have recorded a trace, you can calculate the CPU load for individual functions, for individual tasks, but you can also calculate the CPU load for your core as a whole. So you can kind of get the load, the utilization of a specific core on your microcontroller. But yeah, and that's a really common use case. So good question.
All right. So we have so many questions, but I think it's pretty difficult to answer all of these questions here. So what we do is we'll get back to you people individually on an email by answering your questions. Thank you so much for joining this webinar. Thank you.
Okay, thank you very much from my side too. Thank you very much for setting this up, Raven. I appreciate it. And yeah, we are all looking forward to hearing from you and help you with your timing analysis challenges.
Thank you.
All right. Thank you very much. Bye-bye, everyone.
Thank you, Felix.